the video series of data mining and business intelligence. So today's our topic is clustering. So let's get started. Cluster analysis, or simply clustering, is the process of partitioning a set of data objects, or we can say observations, into subsets. Each subset is a cluster such that objects in a cluster are similar to one another, yet dissimilar to objects in other clusters. The set of clusters resulting from a cluster analysis can be referred to as a clustering. In this context, different clustering methods may generate different clustering on the same data set. The partitioning is not performed by humans but by the clustering algorithm. Hence, clustering is useful in that it can lead to the discovery of previously unknown groups within the data. Cluster analysis has been widely used in many applications such as business intelligence, image pattern recognition, web search, biology, and security. So let's discuss in business intelligence. Clustering can be used to organize a large number of customers into groups where customers within a group share strong similar characteristics. This facilitates the development of business strategies for enhanced customer relationship management. Moreover, consider a consultant company with a large number of projects. To improve the project management, clustering can be applied to partition projects into categories based on similarity so that project auditing and diagnosis can be conducted effectively. In image recognition, clustering can be used to discover clusters or subclasses in handwritten character recognition systems. Suppose we have a data set of handwritten digits where each digit is labeled as either 1, 2, 3, 4 and so on. Note that there can be a large variance in the way in which people write the same digit. For example, take the number 2. Some people may write it with a small circle at the left bottom part, while some others may not. We can use clustering to determine subclasses for digit 2, each of which represent a variation on the way in which digit 2 can be written. Using multiple models based on the subclasses can improve overall recognition accuracy. Clustering has also found many applications in web search. For example, a keyword search may often return a very large number of hits due to the extremely large number of web pages. Now, what is hit? Hits are the pages relevant to the search. Clustering can be used to organize the search result into groups and present the result in a concise and easily accessible way. Moreover, clustering techniques have been developed to cluster documents into topics which are commonly used in information retrieval practice. As a data mining function, cluster analysis can be used as a standalone tool to gain insight into the distribution of data, to observe the characteristic of each cluster, and to focus on a particular set of clusters for further analysis. Alternatively, it may serve as a pre-processing step for other algorithms such as characterization, attribute subset selection, classification, and etc., which would then operate on the detected cluster and then select attributes or features. Because a cluster is a collection of data objects that are similar to one another within the cluster and dissimilar to objects in other clusters. A cluster of data objects can be treated as implicit class. In this sense, clustering is sometimes called automatic classification. Again, a critical difference here is the clustering can automatically find the groupings. This is a distinct advantage of cluster analysis. Clustering is also called data segmentation in some applications because clustering partitions large set into groups according to their similarity. Clustering can also be used for outlier detection, where outliers may be more interesting than common cases. Applications of outlier detection include the detection of credit card fraud and the monitoring of criminal activities in electronic commerce. For example, exceptional cases in credit card transactions such as very expensive and infrequent purchases may be of interest as possible fraudulent activities. Clustering is known as unsupervised learning because the class label information is not present while performing clustering. For this reason, clustering is a form of learning by observation rather than learning by examples. Data clustering is under development. Contributing areas of research include data mining, statistics, machine learning, spatial database technology, information retrieval, web search, biology, marketing, and many other application areas. Owing to the huge amounts of data collected in databases, cluster analysis has recently become a highly active topic in data mining research. So let's discuss the requirements of cluster analysis. Here is a list of typical requirements of clustering in data mining. So let's start with first one, that is scalability. Many clustering algorithms works well on small data sets containing fewer than several hundreds data objects. However, a large database may contain millions or even billions of objects, particularly in web search scenarios. Now, clustering on only a sample of a given large data set may lead to biased results, and therefore, highly scalable clustering algorithms are needed. Second is ability to deal with different types of attributes. Many algorithms are designed to cluster numeric data, that is called interval based data. However, applications may require clustering other data types such as binary, nominal, categorical, and ordinal data, or maybe mixtures of these data types. Recently, more and more applications need clustering techniques for complex data types such as graphs, sequences, images, and documents. Next is discovery of clusters with arbitrary shape. Many clustering algorithms determine clusters based on Euclidean or Manhattan distance measures. Algorithms based on such distance measures tend to find spherical clusters with similar size and density. However, a cluster could be of any shape. Consider sensors, for example, which are often deployed for environment surveillance. Cluster analysis on sensor readings can detect interesting phenomena. We may want to use clustering to find a running forest fire, which is often not spherical. It is important to develop algorithms that can detect clusters of arbitrary shape. Next is requirements for domain knowledge to determine input parameters. Many clustering algorithms require users to provide domain knowledge in the form of input parameters such as desired number of clusters. Consequently, the clustering results may be sensitive to such parameters. Parameters are often hard to determine, especially for high dimensionality data sets and where users have yet to grasp a deep understanding of their data. Requiring the specification of domain knowledge not only burden users but also makes the quality of clustering difficult to control. Next is ability to deal with noisy data. Most real-world data sets contain outliers or missing or unknown values. Sensor readings, for example, are often noisy. Some readings may be inaccurate due to the sensing mechanism, and some reading may be noisy due to interference from surrounding objects. Clustering algorithms can be sensitive to such noise and may produce poor quality clusters. And therefore, we need clustering methods that are robust to noise. Next is incremental clustering and insensitive to input order. In many applications, incremental updates, that is representing newer data, may arrive at new time. Some clustering algorithms cannot incorporate incremental updates into existing clustering structures and instead have to recompute a new clustering from scratch. Clustering algorithms may also be sensitive to the input data order. That is, given a set of data objects, clustering algorithms may return dramatically different clustering depending on the order in the objects are presented. Incremental clustering algorithms and algorithms that are insensitive to the input order are highly needed. Next is capability of clustering high dimensionality data. A dataset can contain number of dimensions or attributes. When clustering documents, for example, each keyword can be regarded as a dimension and there are often thousands of keywords. Most clustering algorithms are good at handling low dimensional data, such as datasets involving only 2 or 3 dimensions. Finding clusters of data objects in a high dimensional space is challenging, especially considering that such data can be very sparse and highly skewed. Next is constraint based clustering. Real world applications may need to perform clustering under various kinds of constraints. Suppose that your job is to choose the locations for a given number of new ATMs, that is automatic teller machines, in a city. Now, to decide upon this, you may cluster households while considering constraints such as the city's rivers and highway networks and the type of number of customers per cluster. A challenging task is to find data groups with good clustering behavior that satisfies specified constraints. And the last is interpretability and usability. Users want clustering result to be interpretable, comprehensible, and usable. That is, clustering may need to be tied in with specific semantic interpretations and applications. It is important to study how an application goal may influence the selection of clustering features and clustering methods. So in today's lecture, we had a brief introduction to clustering as well as we had a discussion about the requirements for clustering. And that's it for this lecture. Thank you.